Hello everybody. I have a new way of recording things here, so I'm going to describe the notes on a PDF and then you get a little corner of my face staring at the camera. So sorry if that's disconcerting. So this was our first reaction. We had copper 2 sulfate, which was the blue liquid, and then we had the iron, which was the nail. And then we know that the copper solid was forming because the nail turned a brown color. And then the iron was going into solution to make iron 2 sulfate. And we know that because the blue color faded. So the copper ions, copper 2 is blue, iron 2 is colorless. So that's our reaction. It ends up being balanced just as is. Now for some of these it would be very hard for you to predict the product, so don't worry, we won't ask you to do that usually unless it's something very common. But still we'll be able to use these reactions and at least classify them. As I'll talk about later, this is called a single replacement reaction because basically you're replacing a single thing, the copper, with one other thing, the iron. Okay, then we had the silver nitrate, which was colorless liquid with the copper, and that turned blue, so we know we're forming copper 2 ions again, which the copper 2 compound would be copper 2 nitrate. Sorry, there's a little 2 down there, but it got written over with the parentheses. So CuNO3 sub 2. And then silver, and we needed a 2 there to balance it. That's also a single replacement. We're replacing the silver with copper. Then we burn the magnesium. So any combustion is fuel, in this case magnesium metal, plus oxygen. And fuel plus oxygen gives, in this case, magnesium oxide. And we know magnesium is a 2 plus because it's in the second column on the periodic table. So MgO is your product because we know oxygen is 2 minus. Because of the column that it's in. This is called a synthesis reaction because you're synthesizing two things or combining them into one thing. Then we had the copper 2 sulfate pentahydrate, which was that blue solid that we heated and it became a clear solid. And that clear solid is a copper 2 sulfate without the water. So the copper ions lose their color when they're dehydrated, when the water is gone. In this case, it's coming out of the crystal. That's called decomposition because you have one big thing that's decomposed into smaller things. And then synthesis, when we added the water to the white solid, it became blue again. So we know we're hydrating our copper 2 ions and the color comes back. So that's another synthesis. It's different from the combustion synthesis because it's not just combining oxygen. Here we're combining with water, and that's called hydration when you're adding water to a compound in a reaction. Then we had the hydrochloric acid with zinc, and we got bubbles, so we know that's a gas, and hydrogen gas is the most obvious candidate, and indeed that's what it ends up being. So then the hydrogen must have left the hydrochloric acid, and the sensible thing here would be we're making zinc chloride. Zinc we know is a +2 ion, and so you get ZnCl sub 2. And then when we lifted the splint to the gas that was forming, that's hydrogen plus oxygen combustion, which is another combustion synthesis, so we end up with water. Then our last two reactions, we had the two clear liquids with barium chloride and sodium sulfate, and we got the white solid, and we know that that is barium sulfate, and then sodium chloride, so salt water. This is called a double replacement because you're basically swapping partners in both ways. So the positive, the barium from the one, goes with the negative, the sulfate from the other to make barium sulfate. And then the positive from the other, so the sodium, goes with the negative from the one, so sodium chloride. So it's a double replacement, replacing the barium with sodium and replacing the sodium with barium. They're swapping partners. Similarly, with the sodium hydroxide and the copper 2 sulfate, we end up with copper 2 hydroxide and sodium sulfate. And we know that because we have this cloudiness happen. So we know we're making a solid in there. This is also a double replacement because the sodium and the copper are replacing each other with the hydroxide and the sulfate. All right. So classification, I kind of did this for you, but you can go back and look and see how things are grouped together. If you want to pause the video and go back and look at the notes and see if you can spot this pattern. Otherwise, 1, 2, and 5A were the single replacement, where I'm just replacing the copper with the iron, just replacing the silver with the copper, and 5A, just replacing the hydrogen with the zinc. So that's single replacement. 3, 4B, and 5B are all similar in that you're combining smaller elements or molecules to form larger ones. So that's synthesis. We're combining the fuel with the oxygen to make the oxide, or we're combining the salt with the water to make the hydrated salt, or we're combining another fuel with oxygen to make another oxide. In this case, it's water. 4A is unique. That's the only decomposition we have where you have a large molecule, in this case that hydrate, falling apart into two simpler molecules. And then 6 and 7 are similar in that they both have the swapping of partners going on. So barium and sodium swapping places, so a double replacement. Sodium and copper swapping places, a double replacement. All right, and then the reaction types by analogy. You could probably do this yourself. I'll do the first one for you, and then you could pause the video and try and do the rest yourself. But imagine you have a chocolate cream-filled cookie and a vanilla cream-filled cookie. I didn't have the cookies laying around, so I'm using these blocks again. So a vanilla cream-filled cookie, if the yellow squares are the vanilla like discs of the cookie, and then the white square in the middle is the cream filling, then a vanilla cookie would look like this. And decomposition would be like when you twist it to tear it apart. So usually the cream stays with one of the wafers or discs, and then the other disc is by itself. So you're going from a bigger thing and decomposing into a smaller thing. All right, so pause the video, see if you can do the rest. Okay, you're back. So synthesis would be the opposite of decomposition. So you start with the cookie torn apart and you put it together. So going from small things to a larger thing. A single replacement would be like if you had the vanilla cookie and you replaced one of the vanilla discs with a chocolate disc. That would be a single replacement. Or a double replacement, this isn't quite the same as what we usually see chemically, but I guess it works. If you have a vanilla cookie and a chocolate cookie and you replace or you swap partners, one of the vanilla squares with one of the chocolate squares, then you get chocolate filling vanilla, vanilla filling chocolate, which these two are the same. So V2F plus C2F going to 2 VFC. I mean, like I said, this is a little different from what usually happens chemically because we have both fillings the same, and usually our ions will be different on the two. So like if we go back to here, we had barium chloride and sodium sulfate. So chloride and sulfate instead of both, the cream filling. Anyway, so here's some practice problems, and I'll just talk you through these. So magnesium reacts with sulfuric acid. So this is going to be a single replacement where the hydrogen from the sulfuric acid replaces the magnesium, so you get magnesium sulfate and then hydrogen gas. So the equation is just balanced as is. How would we know it's a chemical change? Because we'd see the bubbles of the hydrogen gas. So this is similar to when we had the zinc with the hydrochloric acid. Here we've got magnesium hydroxide and hydrochloric acid. So I know that this would form magnesium chloride and water. It's easier to see when you write it out as the chemicals. So magnesium hydroxide is a base, and you use that when you have an upset stomach sometimes. So hydrochloric acid here. And this one would be a double replacement. So basically the magnesium is replacing the hydrogen and vice versa. So you get magnesium with the chloride, and I know that it's a +2 for magnesium because it's in the second column, and chlorine is -1, so I need 2 of those, and then to make it neutral. And then I have a hydroxide, which is -1, with a hydrogen, which is +1, and that together makes water. This is a typical pattern where the acid-base neutralization base plus acid gives salt plus water. All right, I'm going to leave these examples to you to try, but I will post the answers to those. And then just some questions at the end here to run through these. What types of substances are seen in reactants of decomposition reactions? So only compounds work. Remember, reactants are on the left-hand side. For decomposition, you couldn't have an element because an element can't decompose into something simpler. So here's our example from the reactions we did with the copper 2 sulfate pentahydrate, falling apart into something simpler. In a single replacement reaction, do any of the atoms change their charge? Yes, if you think about it. So here's the silver nitrate with the copper, and that changes to copper 2 nitrate with the silver, but here the silver is a neutral solid, whereas over here it must have been Ag plus ions to go with the NO3 minus ions. In double replacement reactions, do any of the atoms change their charge? The answer is no, and you can go back and look at our examples and see for yourself. And then these last two, a student did something wrong in this reaction, and the problem is calcium we know is a +2 charge because it's in the second column. Oxygen we know is a -2 charge, so to be neutral you need just one of each, so it can't be CaO2, it needs to be CaO as a product. So then to balance it we need some 2's in there. Likewise, it's also incorrect to just do this. Ca plus O goes to CaO because oxygen we know comes as O2 molecules in its pure form. You don't usually have just O atoms. That's not stable. Try and draw a Lewis dot structure and you'll see that you don't have filled octets. So again, we need Ca plus O2, so then you need some 2's in there for it to balance. All right, that's it for today. So you can go back and take a look at the actual notes, and I will see if you can do these for yourself, and I'll post solutions.